Today we are going to talk about the derivation of integrated rate equations for zero order reactions. In our previous class we have already seen how to write the differential rate equation for both first order as well as for zero order reaction. So in order to integrate these rate equations, there are certain steps which we need to follow. But before that, why do we need to integrate the differential rate equation? So we integrate the differential rate equation to give a relationship between the directly measured experimental data, that is concentrations at different times, and rate constant. The integrated rate equation is used to determine the rate constant of the reaction, that is the value of K, for either zero order or for first order. Also, it is helpful to calculate the exact time when the reaction is either complete, that is 100% reaction has taken place, or at any intermediate position when the reaction is either 25% or 50% or 90% complete. Then the time taken for completion of reaction to that extent, that can also be calculated with the help of integrated rate equations. The integrated rate equations are different for reactions of different reaction orders. Means the integrated rate equation for zero order will be different, for first order it will be different, and likewise for the higher orders also it will be different for each reaction. When the order is changing, the integrated rate equation also changes. Hence we need to derive such expression individually for each of the reactions which have different orders. But for all zero order reactions, the integrated rate equation will remain the same. For all first order reactions, the integrated rate equation will remain the same. That is, we derive it once and then we can apply the same equation to all zero order reactions or to all first order reactions. Now let us proceed. First we are going to start with zero order reactions, how to derive the integrated rate equations. So a reaction with zero order means that the rate of reaction is proportional to zero power of the concentration of reactant, that is, it is independent of the concentration of the reactant. And if we are considering a general reaction where reactant R is changing into product P, then for that the rate expression, the differential rate expression, can be written as rate is equal to minus dR by dt equal to K into R raised to the power 0. Now where dR is the small change taking place in the concentration of the reactant, dt is the small change in time, K is the rate constant, and R is the concentration of the reactant. Now we know that anything raised to the power 0 is equal to 1. So in this expression we have raised the concentration of R to the power 0. So it will be equal to 1. So now the differential rate equation changes into rate equal to minus dR by dt equal to K. This can be rewritten as dR is equal to minus K into dt. Now we are going to integrate the differential rate equation, and when we integrate on both the sides, then dR changes into R and minus K dt changes into minus kt, and we get a constant there known as the integration constant. So the integrated equation that we have obtained after integrating the differential equation for zero order is R is equal to minus kt plus I. Now what is the value of the integration constant I? In order to derive that value, let us take time t equal to 0, means when the reaction has not yet commenced. Then at that time the concentration of the reactant, we call it as initial concentration of the reactant, and we denote it by R naught. So at time t equal to 0, concentration of the reactant R is R naught, where R naught is the initial concentration of the reactant. Now we'll put these two values, that is the value of t equal to 0 and R equal to R naught, in the integrated equation derived above, that is the equation 1. So in place of R we write R naught, and in place of t we write 0. So equation becomes R naught equal to minus K into 0 plus I. Now K into 0 is 0. So what you get here finally is R naught equal to I, or you can say I is equal to R naught. So the value of integration constant I is R naught. Now I'll put this value of I in the equation 1, and what we get now is R is equal to minus KT plus R naught. That is the integrated rate equation for zero order reaction. And you can further simplify this equation by rewriting it in terms of the rate constant K. So when you rewrite it, K becomes equal to R naught minus R divided by T, where K is the rate constant, R naught initial concentration of the reactant, R concentration of the reactant at time T divided by time T, which is the time in which the concentration has changed from R naught to R. So this third equation will be the finally derived expression for the rate constant value for zero order reaction, and it is the integrated rate equation form. Now if you compare this equation 2, what is equation 2? We just now saw equation 2 is R is equal to minus KT plus R naught. So if you compare that equation with the straight line equation y is equal to mx plus c, then you will see that if you are plotting concentration of R on the y-axis and you are plotting time along the x-axis, then you will get a straight line, and this straight line will be having a negative slope. That is, it will be sloping downwards, and the intercept of this straight line, the intercept means the straight line where it is cutting on the y-axis, the point at where it is cutting on the y-axis, that will represent the value of R naught. And if you calculate the slope of this straight line, it will be giving you the value of K. So slope is equal to minus K, intercept is R naught, and this is the case when you are plotting a graph of concentration versus time. If you get this kind of a graph, then you can predict the order of reaction even if it is not given that it is a zero order reaction, because such type of a graph between concentration and time will be obtained only for zero order reactions. So sometimes you may get questions where only graphs are given and they may ask you to predict the order of reaction. So for such type of questions, you have to pay attention on the graph, what are the variables which are being plotted there, what is taken on y-axis, what is taken on x-axis, what is the nature of the curve, whether it is straight line or not, then whether it is a negative slope or a positive slope, and whether there is some intercept or not. And if the graph looks like what is shown on the screen, then you can easily say that it is a zero order reaction. Now, these are two examples of zero order reactions. First one is decomposition of gaseous ammonia on the surface of platinum, which is acting as a catalyst here, and ammonia decomposes into gaseous nitrogen and hydrogen. 2 moles of ammonia giving you 1 mole of nitrogen and 3 moles of hydrogen gas, and this is occurring in the presence of a catalyst which is platinum. So this reaction follows zero order kinetics, that is, it is independent of the initial concentration of the reactant, which is ammonia. Then second example is thermal decomposition of hydrogen iodide on the surface of gold. This also takes place at a high temperature. Here 2 moles of hydrogen iodide decompose to give 1 mole of hydrogen and 1 mole of iodine. Again, since it is a zero order reaction example, so that means that the rate of reaction is independent of the initial concentration of the reactant, which is hydrogen iodide in this case. So whether you increase the concentration of the reactant or you decrease, the rate of reaction will remain constant, or the rate constant will not change. That is what is meant by zero order reaction.